So let's start the video lecture. The Stern Gerlach experiment demonstrated that the spatial orientation of magnetic momentum is quantized. So this is the direct evidence for the existence of the magnetic moments of atoms, and this was first explicitly demonstrated in 1921 by Otto Stern and Walter Gerlach. An atomic scale system was shown to have intrinsically quantum properties. This is intrinsic because it remains same. In the original experiment of the Gerlach experiment, silver neutral atoms were used and sent through a specially varying magnetic field, which deflected them before they struck a detector screen such as a glass slide. So in this figure, you can see that this this is a furnace which is creating the silver atoms, and this is an arrangement for the production of inhomogeneous magnetic field. What the observed result is this discrete accumulation of the silver atoms rather than a continuous distribution. This is because of their quantized spin. So this is the experimental setup. The principle of this Stern Gerlach experiment. This experiment is based on the behavior of a magnetic dipole, that is atomic magnet in this case, in a non-uniform magnetic field. As in a uniform magnetic field, the dipole experiences a torque that tends to align the dipole parallel to the field. If the dipole moves in a field perpendicular to it, the dipole will trace a straight line path without any deviation. But in an inhomogeneous magnetic field, the dipole experiences, in addition, a translatory force. Therefore, if the atomic magnet flies across such an inhomogeneous magnetic field normal to the field direction, it will be deviated away from its rectilinear path. In the Stern Gerlach experiment, a photographic plate recorded the shape of the beam first in the absence of inhomogeneous magnetic field, then in the presence of magnetic field. In its normal state, the entire magnetic moment of a silver atom is due to the spin of only one of its electrons. In an inhomogeneous field, each pole of the dipole is subject to a force of different magnitude, and therefore there is a resultant force on the dipole that varies with its orientation relative to the field. Classically, all orientations should be present in a beam of atoms and hence be a broad trace on the photographic plate or glass slide instead of a thin line formed without any magnetic field. Here you can see that the experimental result, what we found through the experiment is this, and expected classical result is this, and the quantum expectation result is this. And when we expect The result, according to quantum theory, taking into consideration the decrease of magnetic field del V by del Z in xy plane, then the result should be like this. And this is the result in the absence of magnetic field. Stern and Gerlach found, however, that the initial beam split into two distinct parts that correspond to the two opposite spin orientations in the magnetic field permitted by space quantization. And there is also result for some other atomic beams that were performed by the Stern and Gerlach using atomic beams of other elements. It was found that all elements with magnetic moment mu is equal to mu v, for example, lithium, sodium, potassium, copper, gold, etc., gave doublet with splitting converging on both ends like this. On the other hand, no splitting has been observed for atoms with magnetic moment mu is equal to 0, and these atoms are zinc, cadmium, mercury, lead, etc. Now we'll discuss about the experiment using particles with spin plus half or minus half. If the experiment is conducted using the charged particles like electrons, there will be a Lagrange force that tends to bend the trajectory in a circle. This force can be cancelled by an electric field of appropriate magnitude oriented transverse to the charged particle's path. Electrons are spin-half particles. These have only two possible spin angular momentum values measured along any axis, that is, plus h cross by 2 or minus h cross by 2, a purely quantum mechanical phenomena. Because its value is always the same, it is regarded as an intrinsic property of the electrons and is sometimes known as intrinsic angular momentum. If one measures the spin along a vertical axis, electrons are described as spin up or spin down based on the magnetic moment pointing upward or downward respectively. If you want to mathematically describe the experiment with spin half particles, it is easiest to use Dirac's bracket notations. We have discussed already what are the Dirac's bracket notations. You can watch this bracket notations video lecture by clicking on the I button of the right corner of the screen. Also, I will provide the video lecture link in the description box. You can watch there. As the particles pass through the Stern Gerlach device, they were deflected either up or down and observed by a detector which resolves to either spin or spin down. These are described by the angular momentum quantum number J, which can take on one of the two possible allowed values, either plus h cross by 2 or minus h cross by 2. The act of observing or measuring the momentum along the z-axis corresponds to the operator Jz. So if we want to measure the momentum along z-axis, we will use the operated angular momentum Jz. In mathematical terms, the initial state of the particle is given by ket psi is equal to C1 ket psi j h cross by 2 plus C2 ket psi j is equal to minus h cross by 2, where C1 and C2 are complex numbers. This initial state spin can point in any direction. The squares of the absolute values C1 square and C2 square determine the probabilities that for a system in the initial state ket psi, one of the two possible values of J is found after the measurement is made. The constants C1 and C2 must also be normalized in order that the probability of finding either one of the values be unity. That is, we must ensure that absolute values of C1 square plus C2 square is equal to 1. However, this information is not sufficient to determine the values of C1 and C2 because they are complex numbers. Therefore, the measurements yields only the squared magnitude of the constants, which are interpreted as the probabilities. Now we will discuss about the theory in details. Let us consider the atomic beam consists of atom with magnetic moment mu. When atomic beam passes through pole pieces, it is subjected to a magnetic induction field B. The beam interacts with B through its magnetic moment mu. As a result of this interaction, the potential energy of the atom is changed by U m is equal to minus mu dot B, which is equal to minus mu B cos of theta. If the magnitude of the magnetic field is varied in z direction, that is, if there is a strong field gradient dB by dz, the magnetic potential energy of the atom will also vary with position of the atom, and there will be a force on the atom whose direction will depend upon the sign of cos theta. The atom will be pulled up or down by a force given by F z is equal to minus del u m divided by del z, which is equal to mu cos of theta del b by del z. Now let small l be the length of magnetic pole piece in x direction and v is the velocity of the atom in this direction, and let m is the mass of the atom and t is the time of travel of the atom through the field. Therefore, t is given by distance by velocity. Now, acceleration acting on the atom in z direction will be given by Fz by m. Hence, the displacement of the atom relative to initial direction of the movement on emerging out of the field after time t will be given by dz is equal to ut plus half at square, that is equal to 0 plus half fz by mt square, as initial velocity in z direction is 0, therefore u is equal to 0. Now it is written as half mu cos theta by capital M del B by del Z into L by V whole square. After coming out of the field, the atom will proceed in x direction with velocity v, and in z direction with velocity vz. Let L is the distance between the glass plate and the nearest end of the pole pieces. L is the distance between glass slide or plate and nearest end of pole piece. Then the total displacement capital dz is equal to small dz plus vz into L by V time, that is equal to dz plus fz by m into t into L by V. This is capital L, which is equal to dz plus mu cos of theta divided by m del b by del z into t into L by V, where Vz is equal to Fz by m acceleration into time. Therefore, total displacement dz is equal to small dz plus mu cos theta by m into del v by del z into t into L by V. Total dz is equal to small dz plus mu cos of theta m del b by del z small l by v into capital L by v. Substituting the values for small dz, 1 by 2 mu of mu cos theta by capital M del v by del z into L by v whole square plus mu cos theta by capital M into del b by del z L by v into capital L by v, which is equal to 1 by 2 mu cos theta is common and del v by del z is also common. So we will take del V by del Z to L by V whole square plus L by V into 2L by V, which is equal to 1 by 2 L by V whole square into 2L plus L by M into L del V by del Z mu into cos of theta. This is the total displacement of the beam from its x direction while coming out from the pole pieces at distance capital L. It is important to note that it is clear from the above expression that atoms for which mu is equal to 0, the displacement will be 0, and so far mu is equal to 0, total displacement is equal to 0. Second, the atoms with its magnetic moment mu directed horizontally, that is, if theta is equal to 90 degree, then it will go straight. That is, there is no deviation. Point number 3 is an atom with magnetic moment in exactly vertical direction, that is, if theta is equal to 0 degree, will be placed upward, and if theta is equal to 180 degree, that is an atom whose magnetic moment is downwards, then it will be placed downward. In general, atoms will be displaced according to their vertical component. We are measuring theta from z-axis. Now we will discuss some results. So, under classical approach, according to classical theory, all orientations for mu ranging from theta is equal to 0 to theta is equal to 180 degree are possible. Let us consider mu cos theta is equal to mu b. Then the total deviation on both sides of x-axis, that is delta z, is given by 2 times of the dz, and it is equal to L by V whole square into 2 capital L plus L divided by ml into del V by del Z into mu cos theta, which is equal to L by V whole square into 2L plus L by M into L into del B by del Z into mu B. Hence, the atoms will hit the photographic plate or glass slide at different positions spread in range delta Z. So, this is according to the classical approach. Now, we will take up the quantum approach. So, second is quantum approach. According to quantum approach, all settings or angles are not possible for atomic magnet with respect to magnetic field, but only certain discrete number of orientations are allowed. This is called the idea of space quantization. That is, only certain discrete number of orientations are allowed. We know that magnetic moment mu is given by minus g mu b into j, where j is the total angular momentum quantum number. Small g here is the Landé's splitting factor, and mu b is Bohr magneton. Therefore, the permitted orientations for J are 2J plus 1, and hence permitted orientations for mu is equal to 2J plus 1 about any specified direction. Therefore, about any specified direction. Therefore, dz is equal to half of L by V whole square into 2 capital L plus L divided by M into L del B by del Z G mu B Mj, where Mj is the projection of J in specified direction, and Mj can take values from minus J to plus J. For example, silver, copper, hydrogen, lithium, sodium, and potassium. J is equal to 1 by 2, and hence Mj for these atoms is equal to minus 1 by 2 and plus 1 by 2. And actually we get two traces experimentally also. Now the convergence on both ends on the photographic plate or glass slide is due to decrease of magnetic field with respect to the z direction, that is del v by del z in horizontal plane. The separation between two lines will be given by delta z is equal to L by V whole square into 2 capital L plus small l by capital M into L divided into del into del V by del Z into G mu B, which is equal to L by V whole square 2L plus L by M into L into del B by del Z into 2 mu. Thus, we can get values of mu from above expression after knowing delta Z from the experiment. Harmonovalent since mu is equal to plus minus 1 mu b. So friends, this is for now. We just discussed in this video lecture about the Stern Gerlach experiment, experimental setup, principle behind this experiment, classical and quantum mechanically found results, verified with the experimental results, theory and derivation of the deviation of the beam from its original state path. We all derived the theory and formula in this video lecture and also verified the results classically and quantum mechanically. Friends, hope you liked this video and learnt about the important phenomena of Stern Gerlach experiment and the concept and theory behind this. So friends, just subscribe the Sai Academy channel and press the bell icon and give the thumbs up and share this video lecture with your friends and family members so that they can also enjoy this video lecture. Thank you.